changing. So this is called the time dependent Schrodinger equation. Time dependent Schrodinger equation. And as usual, now you know what is H hat, that is Hamiltonian operator, that is nothing but sum of the kinetic energy operator and potential energy operator. So last class I introduced the operator form or the exact form of that Hamiltonian. So kinetic energy operator plus potential energy operator. So focus only on this part. What I did was that just I gave the expression for operators. Kinetic energy, first term is kinetic energy part and next one is a potential energy. Then the rest is the same. Psi of xt equal to IH cross partial d by dt of psi of xt. So this is a simple form and this is including that operator form. That's only. So this is a time dependent equation, and time independent Schrodinger equation is given by H psi is equal to E psi. H psi is equal to, I may not be reading always this H hat, but when I say H psi, you have to remember that I'm talking about the Hamiltonian operator H hat. So H psi is equal to E psi is the time independent Schrodinger equation. So here I am, you can see that it is time independent. So the wave function is independent of time. So we are not writing explicitly t, psi of xt. Okay, so time independent Schrodinger equations. As usual, this is the kinetic energy plus potential energy part. But what I did was that just I took psi for both kinetic energy part and potential energy part. That means minus h cross square by 2m d square by dx square psi of x plus V of x psi of x equal to E psi energy. This is the time independent Schrodinger equation. There is no time parameter here. So these are two forms of Schrodinger equation. Why we need Schrodinger equation and all that we will see. But you can see that this Schrodinger equation is a second order differential equation. Second order differential equation. Okay. Or in other words, we can say H psi is equal to E psi. So this is a time independent Schrodinger equation and this is a time dependent Schrodinger equation. Time dependent Schrodinger equation tells the evolution of a quantum mechanical system. If you want to calculate with respect to time how it changes, we will get that information. We have to solve that equation information. Now this Schrodinger equation from the classical wave equation. Actually, there is no derivation for Schrodinger equation, but we can get it as it was. Then if there is no derivation, how it is coming? Because that is we can get it from the classical wave equations. Classical wave equation. Because assuming that okay, that time it was known that okay, waves are associated with the particles. So whatever for this quantum mechanical system, so that wave equation, whatever it was in practice, that was in the similar approach, we can get it. So here Schrodinger equation, how we will get it, that you will see here. This is not just a derivation point of view, but for the completeness, I am just discussing. For those who are not interested or not that much want to go into that much deep, then just you can have that time dependent Schrodinger equation and time independent Schrodinger equation, two forms. That is important because that equation we will be using in all of the systems. So irrespective of whether you know the real meaning or exact what it is and all, forget about that. That functional form is important because that functional form we will be using for all the systems. In our in this quantum mechanics problems. So this is just how from the classical wave equation we are getting that equation, just to show that. So here we have a second order differential equation and here we are bringing the de Broglie concept. What it is, what we are doing is that this lambda square we are just giving, connecting this lambda using the de Broglie equations. So as per de Broglie equations, you know lambda is equal to h by p or h by mv. So you have lambda equal to h by mv, but at the same time you know that momentum p is equal to mv or p square is equal to m square v square. So from here, if you expand like that, m square v square, then that is equal to 2m into half mv square, because I'm slowly bringing that kinetic energy and all into this. That means momentum square, that I am expressing it in terms of various energy components. So p square is equal to m square by v square, simple mathematics. So 2m into 1 by 2, so you will get the same as here. And finally 2m into, so half mv square is kinetic energy, so I wrote 2m into ek I got. So kinetic energy is equal to what? The next step what I'm doing is that kinetic energy is equal to total energy minus potential energy. Just an expression I'm bringing, that's only. So what happens? P square, in place of p square, I have an expression 2m into E minus V. Now, in this equation, lambda square means what? Lambda square is equal to h square by p square. H square by p square. So p square, I have this expression. So I will take